final one is for the next step is what? I have did only 2 nuisance factors, right, 2 nuisance factors plus 1 treatment, that is what is your Latin square is. Now I am going to do Greco-Latin square, where I am opening up a Pandora box and saying, look, I am going to accommodate what? Any number of nuisance factors as long as they are independent. This is the highlight, right, because once you start from independent factors blocking, you should be able to block n number of independent parameters. You learnt about 1 which is RCBD, you learnt about 2 which is Latin square. Now you are going to learn about n independent factors, how to block n independent factors, that n could be any number. Now you know how to do replication also. Look at the way we have taken baby steps. ANOVA is the simplest, RCBD complicated, slightly complicated. Now Latin square with replications, replication is a must because degrees of freedom will go down. So you have to do replications. Now you are going to do all factors in one shot, all independent factors, how much ever you give, we will be able to sort it out. That is what is Greco-Latin square, okay. Both Greek and Latins have joined here, so it is Greco-Latin. So you have the idea is you have a P cross P Latin square superimposed on a second P cross P Latin square, in which treatments are denoted by Greek letters. So you have a one Latin square superimposed on the other Latin square, okay. The second Latin square is nothing but treatments, and the first Latin square should have what I call the nuisance. So simple examples. So the Greco-Latin square initially can be used to control systematically 3 sources in 3 directions. The design also allows investigation of 4 factors, okay, and it can be extended for all p greater than or equals to 3 except p equal to 6. I will not get into this all this math formation. You have Latin square for exists for Greco-Latin square exists for all p greater than or equals to 3 except 6, p equals to 6. We will not get into why reason, you can figure it out. So what is the Greco-Latin square design? Rows, columns, 2 letters. So now you have merged actually 2 squares, and what you can do, you can also do 3 squares as well. You can also combine, you can also think of extending this. I am just giving you a simple Greco-Latin square for 3 factors. You can use this idea to extend it for multiple factors. Hardly you will have 4 or 5 multiple independent factors, okay. That is a challenge. There is no point going beyond 3 or 4 factors, because after that you will ideally not have independent factors, you will start having interactions, okay. So therefore we will stop at 3 extraneous factors where we talk about Greco-Latin square, which is a, so you can see this 1 2 3 4 columns, same like Latin, but now you have one more square superimposed on it, okay. I can have one more square also superimposed on it to take care of multiple. So imagine beta A alpha, right, nobody is stopping me from writing A alpha, one more symbol, okay. So total factors will be 5 factors. So now same idea, there is nothing, how many you will have, rows, columns, Latin, Greek and replicates. If I do it 5, if I do replication it will be 5 and then error obviously, clear. So this is your Greco-Latin square design, okay. So this is the ultimate, meaning I could have more 3 factors, and if at all required I could start introducing more square superimposed. The idea is, so you have to understand how we started off from ANOVA, where we had no blocking, no extraneous, only 1 factor, to 2 factor where we had the freedom of choosing rows and columns independent. Then multiple factors, then we consent to have a square design, because only then I could have a Latin square design, only then I could have separation of 3 factors, 2 factors plus 1, 3 factors. Now this is Latin square where we are dealing with 4 factors, okay. Only question is all of them are taken it to be independent, okay. The idea of 4 factors is superimposing 2 Latin squares. Now I could start superimposing multiple Latin squares to extend it to any number of variables as long as they are independent. So in ANOVA you would have only treatments and errors. In RCBD we had treatment, blocks and errors. Now Latin square, treatment, rows, columns, errors, and then with replicates we had replicates. Here you will start having adding more and more depending upon the number of squares you superimpose. That is your Greco-Latin square design. Make sense? Clear? So now there are multiple ways to replicate, that is why I did not give any replication. So the model should be clear now. You have mu, okay, tau j for treatment, theta I for whatever Greek, omega k, phi L, epsilon I j k L, okay, although we have not considered interactions. See all this, one of the things you have to keep in mind, nobody is stopping you from doing mean square block, mean square row by mean squared error. If rows are your treatment, one more set of treatments, fine, you can do. So this is in a way all the factors need not be nuisance also, you could have 2 independent factors, you understand. So this is, that is why you do not even call it as treatments, I say 4 factors, okay. This handles 4 factors, 4 independent factors. You could have all 4 of them important to you, or only one important, or 2 important, or 3 important, it does not matter. Greco-Latin square handles 4 independent factors, the only catch is independence. RCBD handles 2 independent factors. The second one could also be important, it need not be blocks, it could also be other set of treatments. So you could call it as treatment 1, the other could be treatment 2, and in Latin square it could be treatment 1, treatment 2, treatment 3. The only catch is all of them are independent. We are not specifically, if you look at the formula or if you look at the derivations or whatever, we are not specifically saying this should be treatment and the other should be blocks, we never emphasize that. We said these are 3 independent factors, 2 could be nuisance, 1 could be treatment, or all 3 could be treatments, but they are all independent. The only assumption or the only catch in all of this derivations or in our discussions is these variables or these treatments, these factors are independent factors. When you have independent factors, you can go close your eyes and do RCBD ANOVA, one way ANOVA, or all of this. The catch will be how to include interactions.
So in two-way ANOVA we try to estimate the positive effect of that particular treatment.
So two-way ANOVA, what will happen is you will also start considering interactions. That is something which we have not done.
So based on the positive effect or the negative effect, we tend to call it as a treatment or nuisance.
No, need not. It could be just treatments, 2 treatments. It does not matter. See, in our case also RCBD is basically 2 factors. Both of them could be treatments. That is what I am trying to say. Both of them could be treatments. Only thing is you are assuming that there is no interaction, or there is the model does not have a formal way to include interactions. The synergic effects has not captured. So we have not captured so far synergy, okay. We are assuming all of them are independent, and that is why I am saying they are nuisance, because generally nuisance are independent by Gaussianity and by the idea of central limit theorem, okay. They are all independent and they are Gaussian, so we do not consider interactions, we assume independence, and that is why I do not call them as treatments. But when you start looking at treatments, today if you look at drugs, when multiple drugs are given, what is the idea? Do you think they all work independently? Certain drugs go well with certain, so you have a synergy. Either it could be positive, we want it to be positive, but it could also be negative, one could inhibit the other, right. So usually you have positive or negative interactions. So that is why people usually ask for what are you allergic to, what is the medication you are already taking, because drug interactions, that has to be not accounted for. Those ideas are not accounted here, the interaction effects are not accounted here. Clear? So this is, that is why I do not call it as two-way ANOVA, because the interactions are not accounted. Okay, but all independent 4 to 5 or 6 whatever number of factors, you can use the idea of merging Latin squares and doing it. Clear? So far so good. So that brings us to the end of all independence. I have given examples so you can think about it. Okay. So you can start constructing what I call it as a hyper square, like 4 beyond 2 squares now we have merged, we can merge 3, 4, 5, 6. So that is the generic idea, that is the take home message. You can do hyper square and do this. Clear? Make sense everybody? Yeah. So the next class we will start looking at interactions. Okay, we will start looking at interactions in a simple sense, we call it as factorial designs. We will do 2 power 2 factorial, 2 power 3, 2 power k, meaning yes or no questions, either interaction is there or not there. Only we will conduct experiments at only 2 levels, both zeros, both ones, both the factors. Suppose we have 2 factors a and b, how many experiments are possible? You can do it at multiple levels, but if I do only 0 or 1, how many experiments? Only 4 experiments. One factor 0 1, the other factor 0 or 1, the combination is only 2 square, 4 experiments. And if you were to take 3 factors and only 2 levels, how many experiments? 3 factors 2 levels. 2 levels is meaning what? Either you keep the do it at 0% or do the factor at 100%. So either it is like a switch, this factor is on or off. That is the easiest way to figure out interactions. It is a common sense. What is the easiest way to figure out interactions? Will you do experiment at 10%, 20%, 30%? No. What is the easiest way to do experiments? You give dosage only one one dosage and the other one you make it 0, or you give both of them max dosage. So you see the difference, both at max, one max, one 0, then you will know the effect of second, whether there is interaction or not interaction. That is precisely it is. Clear? So we are going to do that kind of simple logical experiment, simple experiments where we say 2 factorial, 2 levels, okay, 2 power k design, we call it as 2 levels, multiple factors. We can do 2 power 2 to understand the effect of interaction of 2 factors. We can do 2 power 3 experiments to understand the interactions of 3 factors, 0 1 all combinations, 2 power 3, that is what we do, 8 experiments. So using simple 2 factorial experiments we will know whether there are interactions or not interactions. Once I complete these experiments, then I will move on to 2-way ANOVA and multiple way ANOVA, because then I know these interactions are not important, these interactions are important. You understand? When you start off you do not know whether interactions are important or not important even, then how do I design how much levels of interactions I should do? First you have to establish the fact that there is interactions among factors, that will be established using 2 factorial experiments. So when you conduct experiments you do not blindly go and say this interaction level, this interaction, no, first establish the fact that whether there are interactions, that is done using simple 2 factorial experiment, 2 power 2, 2 power 3 designs. Once you do and establish which interactions are important, then go on do a full scale experiments with multiple levels of interactions. So interaction itself we have to approach it carefully, first we have to establish whether interactions are there or not, then we should move on to establish the level of interactions, okay, that is how we will proceed. Make sense? Okay, thank you folks.